Okay, so moving on to the second talk of this workshop. We're very happy to have Kevin Jamieson, who is an associate professor in computer science and engineering at University of Washington, or UW. So if you've worked on pretty much anything along the lines of sequential learning, you'll very quickly encounter his name. So, bandits, active learning, hyperparameter tuning, reinforcement learning, very influential works in all of these sorts of topics. And although Kevin's I would say a theory researcher, he's the kind of theory researcher that puts a lot of effort into making things really work in the real world and using real world insights and experience to actually choose the right theory topics, which I very much appreciate. Maybe I should do more myself. We're very happy to hear about reinforcement learning today. And take it away.
Thank you, John, for the introduction, and thank you for the organizers for this invitation to be here. Singapore is a really awesome place to visit, especially in the wintertime for us in the Northern Hemisphere. So today, I really enjoy the format of this workshop, and I was told to spend the first half giving a more sort of tutorial-ish talk about the topic, and today's topic is going to be reinforcement learning, or more generally sequential decision-making. And then the last half is going to be some of the more thorny topics that my research has tried to address over the last several years. And so if you don't know anything about reinforcement learning, it's okay. Hopefully, I will get you up to speed in the first 50 minutes. So over the last couple decades, there has been actually a lot of advancement in the practical reinforcement learning area. And here, the splashy ones with, gameplay and things like this, but also there's also things like no-limit Texas Hold'em and diplomacy and these more complicated cooperative games. But what a lot of these flashy sort of applications have in common is that they've all relied on enormous amounts of computation to actually solve these games. And what I mean by that is in none of these games are actually being learned in real time. Every single one of these applications and almost every big success you've ever seen in reinforcement learning, including self-driving cars, a lot of that work is actually being done in simulation many, many times faster than real time. And this is absolutely necessary because in any of these applications, if you were to have to learn in real time, like a human has to learn in real time, every one of these would have taken millions of years. Or not millions of years, but thousands of years to actually learn these strategies. And the reason why they're so inefficient is because the way that these algorithms actually learn, how they explore their environment and try to interact with their environment, is extremely naive. And what we're going to do over the course of this lecture is try to figure out how do we improve these performances and how do we make better exploration strategies so that we can actually compete with human-level performance and go far, far beyond it. And the reason why it's important to go beyond systems that require simulators to learn faster than real time is because there's many applications in which you can't have a good simulator for yet. The obvious one being healthcare, with designing new drugs and treatments. We need to actually try these on people, and we want to make those treatments as efficient as possible, those experiments as efficient as possible. We don't want to be wasting any time or do anything dangerous. Myself, I work at 20% of my time is spent at Amazon Robotics, where we do a lot of reinforcement learning and trying to put new policies onto these robots. And you'd think that we'd be able to have good simulators for these very well constrained settings, but it turns out that physics simulators are very, very poor at deformable bags. Or if there's liquids inside the bags. We're just extremely bad at simulating these processes, and we really have to do it just in real time, and these are extreme challenges. And so these are the kind of applications that really motivate my work, is trying to do more exploration in real time without a simulator. And so what we're going to focus on today is do a crash course in the frameworks for sequential decision-making. The most common frameworks are multi-arm bandits and Markov decision processes. And then once we're up to speed with a notation and vocabulary, we'll then look at some of the remaining issues, some of the biggest issues remaining in this field, and talk about some of my works that have tried to address some of these shortcomings. So let's jump right in. And just like with Tom's lecture, if you have any questions or comments along the way, feel free to just raise your hand or just shout out at me in case I miss you. So in the multivariate setup, what we're going to have is patients are going to arrive sequentially, and they're all going to have identical symptoms. And the doctor has access to 8 different treatments to treat this disease or these symptoms. And when you assign this treatment A to the patient, you're going to have some outcome between 0 and 1. Let's say it could be 0 or 1, denoting, say, failure or success, or not getting better or getting better, where a higher number is better than a lower number. And we can think of the counterfactuals. Even though each patient is only going to be assigned a single treatment, we can think about the counterfactuals of what would have happened if it would have given any one treatment to that individual. And one thing that will aid us in these counterfactuals is assuming a model, a very simplistic model, that all patients are basically IID. They all behave basically the same. They're random variables of whether they react to the treatment or not, but they're all being drawn from a population, let's say. This is an equivalent sort of parameterization. If they're being drawn from a population, they can all be heterogeneous, but if they're always drawn from that population, it can be modeled as a random variable. And so what we're trying to do is identify the treatment that has, say, the highest expected value, mu A, because that's going to be the best treatment. And we're interested in 2 different things with sequential decision making. The first one being in a healthcare situation, we want to save as many people as possible. These people are coming to us with symptoms and illnesses. We want to give them treatments in order to treat and have as many successes as possible. And so this is going to be the equivalent to maximizing our cumulative reward, maximizing the total number of people that are actually reacting to these treatments in a positive way. And so if this is the outcome, xka is the outcome of an individual treatment to individual k, because of our model, it's a random variable. This sum will concentrate by the law of large numbers, and we can actually just talk about the means of assigning that treatment AK to that kth person that comes to us. And so we're trying to maximize the expected performance over time. And again, implicitly here, we do not have prior knowledge of the means. We do not know how these treatments work, and that's the whole problem. We're trying to identify what is the best treatment. And a second objective is to just identify what the best treatment is. Again, in a healthcare setting, if you're doing clinical trials, before you start doing some adaptive sort of saving as many people as possible in a clinical trial, there's lots of things of just trying to judge efficacy. Does the drug work or not? And you're trying to figure this out as fast as possible. And what we'll see is that these 2 objectives, while extremely related, are actually at odds with one another. The optimal strategy for identifying a very fast or a very good strategy is not necessarily the one that will save as many people in a cumulative way. And when we look at maximizing the cumulative reward, we actually like to measure something called regret, which is equivalent, if maximizing the cumulative reward is equivalent to minimizing the cumulative regret. And all it is the amount of reward that you would have received, which is the sum over mu ak, subtracted from the amount of reward you would have received from the best strategy in hindsight. Okay, there is some treatment that has the best amount of mean, is the most effective drug, and we are comparing ourselves to that drug. And what we'd like to see is that as k gets very, very large, this is trailing off, and if we say do an average regret, if we put a 1 over k, we'd like this thing to go to 0, because we'd like to converge to the optimal strategy over time. Okay, because these are the definitions that we're going to be using throughout this talk. Yes?
What is A star here?
A star, great question. A star is going to denote the best mean, so the highest, the argmax. So I could have put, instead of this argmax over A, I could have put mu A star here. Sorry about that. Yeah? You absolutely can. So at each time k, you get to choose any action you'd like. So at time, patient k comes in, you get to choose any one of the big A actions at any given time. But because the patients are IID, there's no reason to choose. You're trying to explore all the actions at any given time. but you can only choose one action at any given time. And that is correct. Yeah, because they're IID. When I go to an example in a second, I think it'll become clearer. So because these patients are IID, if we look at if we have these A treatments on the x-axis, and we say uniformly allocate some patients to each treatment, then what we're going to have is some empirical average of the performance of each treatment, right? So if TA is the number of times that the treatment A has been assigned, and we have these xKa being that sum being the total number of outcomes of treatment A, then that empirical average is going to be the average amount of reward we get when treatment A is being used. And because this is an empirical mean, it's only been used, we've only shown this treatment a finite number of times, these are going to be noisy estimates. And because we have noisy estimates, the accuracy of these empirical means are going to concentrate approximately like 1 over the square root of the number of times this treatment has been shown. Okay, this is the rate at which the empirical mean converges to its true mean. And clearly, as we grow the number of times we allocate to each treatment, these confidence intervals, because they're going down like 1 over the square root of TA, the 1 over the square root of the number of times that we've assigned this treatment, these confidence intervals are going to shrink over time. And eventually, we're going to be able to distinguish what a good treatment is and what a bad treatment is with high probability. And if we take a very naive strategy of just uniform sampling, so every time a patient shows up, I'm just going to uniformly at random assign a treatment, then each treatment is going to get about the same numbers of samples. All of these confidence intervals are going to be about the same size. And so after I've allocated epsilon minus 2 samples to each treatment, I've taken A epsilon minus 2 total samples. And if I take my argmax, then each confidence interval is going to be about epsilon. And it's easy to show that the performance of that empirical arm, or that empirical treatment, is going to be about epsilon. It's going to be about epsilon good. Now, the issue with this strategy is that if we look at these treatments on the right-hand side here, they are far, far, far below the empirical best strategy. Really, all we really needed to do was get these confidence intervals below the lower confidence bound of our empirical best strategy over here. And so we oversampled these strategies. And what oversampling means is that we were assigning this treatment more often than we should have, and we were assigning this treatment even when we could have known that it was already insufficient. It was already not that great of a treatment, but we kept showing it. This is bad for both the regret and for finding an epsilon good treatment, because it's just wasteful, but it's also you are potentially giving a treatment that you know is already bad. And so in the line of the sequential decision making, one of the most landmark papers is actually from Peter Orr in 2002, where he proposed the so-called upper confidence bound algorithm, or the principle of optimism in the face of uncertainty. And it's a very simple algorithm. What it says is choose some constant c such that the empirical mean minus the true mean is less than or equal to square root of c over the number of times that you've taken that action A, okay, up to the current time. And for the experts in the room, yes, I'm going to be ignoring log factors and things like this throughout this talk. I'm just going for the very coarse sort of quantities here. But morally, I'm going to choose this c such that this empirical mean is concentrating according to that, and that at each time k, I'm going to assign the treatment that has the highest value of this empirical mean plus this confidence bound with this c in it. Okay? And what this has the effect of doing is that now, instead of when we did a uniform allocation, all these confidence intervals were the same size. But now that we're doing this non-adaptive, or we're doing this adaptive sort of scheme of choosing a treatment based on what the empirical and the number of times that we've taken this action, we now have different confidence interval sizes. And if we keep playing this strategy, if we always choose the treatment that maximizes this quantity, it actually has the effect of minimizing the maximum upper confidence bound. And eventually, if we keep playing this strategy, there will be just a single treatment that will keep being played over and over and over. it will converge. So in the beginning, it's sort of exploring everything while it doesn't know everything. But once it updates the statistics, it will eventually only start playing a single treatment, and that treatment will provably be the best action. And this is a little video of how this algorithm actually works. And this is a incredibly successful algorithm. And it's for many, many years, this was basically the only idea we had for sequential decision making in the stochastic setting. And we'll see that more in a moment. But I want to show you why this strategy is so loved by the community. It is because it is so simple to analyze. So if we consider our definition of regret here, the sum of the rewards of mu a star, this is the most reward we could have gotten, versus mu a k, this is the reward we actually got. Then what I can do is I can use my definition of that concentration inequality up there to upper bound this quantity, just replacing mu a star by its confidence bound, using that identity. We know, and so now I have mu hat a star plus its confidence bound. I can upper bound that by the upper confidence bound of at, because by definition, ak was the one that maximized the upper confidence bound at time k. And now I just apply my identity again, because I have that mu hat ak minus mu ak. I do a direct integration, nothing fancy going on there. It's just 1 over square root of I, sum from I equals 1 to n is just square root of n. And I apply Cauchy-Schwarz, and I have a regret bound. And the form of this regret bound is very interesting. So how it behaves is basically the square root of some constant, don't worry about the constants, times the number of actions I have, times the number of time steps I have, the horizon of this game. And so what you can see is that if I look at the average regret, if I divide this by k, I'm seeing that the average amount of times that I'm making a mistake, or the average amount of times that I'm playing suboptimally, is going to 0 quite rapidly. And in fact, a low regret algorithm always immediately applies an epsilon good identification of a treatment. And the way you can see that is if I draw an a hat uniformly at random from all the plays that I played, from a1 to ak, after these k time steps, so these are the actions that I actually played at those given times, if I draw that a hat uniformly at random, it's by the definition of expectation, if I look at the expected value of mu hat a star minus mu a hat, it's just, well, each one happened with probability 1 over k. The sum over k equals 1 to k of mu a star minus mu a k. You recognize this quantity as exactly as the regret, but we already just proved the regret is growing like square root of ak, and so I plug it in and I get square root of a over k. Okay? And so what this says is that if I play this game for k equal to, say, epsilon minus 2 times a, then this right-hand side will be less than or equal to epsilon. And so immediately, this very simple analysis, which is really not skipping that many steps or glossing over that much, of this algorithm called UCB, or optimism, is extremely simple and extremely powerful. And what's more powerful about these is that these are optimal results in a worst-case sense. For the worst-case instance, meaning the worst-case setting of these means or treatments, nature can come up with the worst-case treatments of these. And in that worst-case sense, no algorithm can do much better than these results. Meaning no algorithm gets substantially less regret, and no algorithm can identify an epsilon good alternative with fewer samples. But it is in a worst-case sense. And what I really want to drive home in this talk is that nature is not adversarial. Nature is very far from adversarial often. Sometimes it gives easy cases, sometimes it gives hard cases. And we want to adapt, provably, to these easy and hard cases. And if we actually look at the behavior of this algorithm, if we define this gap parameter, delta A, as mu a star minus mu a, this is the suboptimality gap of assigning mu a star versus mu a. Okay, this is how much we're losing by playing action A instead of A star. And if we just sort of squint at how this algorithm is behaving, by the law of large numbers, the best alternative is going to converge to its true mean mu A star, all of these are going to converge approximately to mu a, their respective means. And so the difference between these, in the size of this confidence interval, the way that this works, is going to be about the same size as delta A. And by some simple manipulations, we can conclude that for all time, the total number of times we're ever going to play a suboptimal arm is going to be bounded by 1 over delta A squared. Okay? We're never going to keep playing suboptimal arms. We're eventually going to stop playing them at some time. And it's a very powerful result because what we can then conclude is that we can immediately improve our regret bounds using these facts in our sample complexity bounds. First, we know by what I just said, we know we're never going to play a suboptimal alternative A more than 1 over delta A squared times. Thus, we can say that the sample complexity is no greater than this quantity here. And moreover, because if I'm playing an alternative 1 over delta A squared times, at each time I am incurring delta A regret, the total regret I'm going to incur is just the sum over all actions of the inverse of delta A times this log k, where the log k is accounting for a union bound. That is not too important for the purposes of this conversation. And we call these results instance-dependent results. Okay? And why we call them that is because the regret bound that you get and the sample complexity that you get depends on the properties of the means themselves. Okay? And so what it means is that if nature chose some set of means, these algorithms are, if those gaps delta A were very, very large, this is going to be a much smaller sample complexity and a much smaller regret. If the means were were chosen very adversarially, such that those delta A's are very small, those gaps are very small, then that's a very hard instance, and we can't do anything better than the worst case, and then we fall back to that minimax or worst case results. And what we can show is that these are actually provably optimal. There exists no other algorithm that can do substantially better than this. And this is important because what we've shown is that these algorithms are provably adapting to the true difficulty of the problem. If the problem is easy, it will take advantage of that and perform better. If it is hard, it will take as many samples as it needs. Okay? And so this is sort of the story for multi-arm bandits. It's a very simple setting. And this is used everywhere. So if the world of A/B testing is often actually using multi-arm bandits. And there are literally tens of thousands of tests going on your phone at any given time on a variety of Spotify or Meta or Google. There are tens of thousands of tests going on at any given time using this technology, using this algorithm, or algorithms very inspired by this approach. It is literally everywhere that you touch the internet, and you never knew it. And it is all based on these principles. But these are also the simplest possible problem. This is you have A alternatives. It's a stochastic model. It's a very simple sort of problem, but it's nice to know that we have optimal results for it. And so before moving on to a more advanced setting, I just want to pause here and see if there's any questions about the multi-arm bandit framework. Because this is going to be the basis for moving into more interesting settings where we are talking about reinforcement learning and robotics and things like this. Okay, great. Everyone's on board. So of this setting, this multi-arm bandit framework, there's many downsides to it. There's many weaknesses of it. First of all, this idea that everyone shows up with the same symptoms. This is extremely naive. I mean, people show up with all sorts of symptoms. A vet has to deal with a monkey, a cat, a dog at any given time. They need to know everything. They need to adapt to everything. But more interestingly, when I go to the doctor and I'm given an antibiotic and it doesn't work, if I'm still sick in 2 weeks, I'm going back to the doctor. And that doctor has to react in some way. I don't just go away. But that doctor now has this piece of information that I was given that treatment and it didn't work. And that can be information that can be used to decide what kind of other antibiotic or what kind of other treatment might actually be useful. And moreover, I might have some extremely complicated treatment process that has a schedule of how I should be scheduled dosages over time. And maybe during the course of this process, I get some lab results, and maybe I see my liver's failing. Well, certainly they're going to stop the process or change me to a different drug. And so how do we incorporate that kind of temporal component into this framework? And the answer is a Markov decision process. So here, the game is going to look slightly different. So now patients are now going to arrive with some observable state S1. And so this is like your list of symptoms, let's say. And then let's say the doctor still has the same set of treatments available to them. This could be a very large set of treatments. But now, when you assign some treatment A1 to the patient that just came to you, you're going to get some outcome XS1A1. So it's basically just the reward at that time in response to being in state S1 and receiving action A1. And more interestingly, now the patient is going to transit to some other state, some new state S2. Okay? And this new state S2 could be the result of, you were given an antibiotic and maybe it didn't work and now you're septic. Or you're given that antibiotic and now you have toxicity and you're losing your hearing. There's all sorts of things that could, or you got better, all sorts of things that could have happened during that process. And then you're going to repeat this for big H time steps. Okay? So you're going to be given this treatment, you're going to evolve your state, and then you're going to get a new state, you're going to get a new treatment, evolve your state, and so on and so forth, until you hit this big H time steps, and you get your final sum reward of all the action of all your rewards over the time steps. And it could be, in the medical setting, it could be maybe you're getting no reward along the way, and you only get a reward of that last time step. That's totally allowed. So you're getting no sort of signal until the very, very end at this long horizon. And now the doctor in this setting can now be thought of as a policy where what they're doing is they're trying to learn some mapping from the particular state that you're in at time H to the particular action that she is prescribing at that particular time. In the model here, as in multivariate bandits, we're going to say that yes, the rewards at any given time are going to be an expectation equal to some reward function that is going to be unknown, and that the next state is going to be drawn IID from some probability distribution that depends on the current state and action that was given. Okay, so arbitrary dynamics are allowed here within this discrete state action space. Okay, and so the difficulty, I've just rewritten this problem in a more sort of formal way, or abstract way. And the difficulty of reinforcement learning is that prior to playing the game, you have no idea what the reward function is, and you have no idea what the transitions are. So you have no idea what's going to happen if you give that treatment, what's going to happen with this patient, and you need to figure that out. And so what we're going to do is we're going to start with in this framework, we consider to have a finite set of policies. These could be all mappings from states to actions. It turns out that the deterministic set of policies is optimal. We don't need to consider stochastic policies. And we're going to define the value of policy pi as just the summed expected reward of rolling out that policy. Meaning if the doctor adopts that policy pi, and then every time they see some state SH, they apply AH equal to pi h of SH. Okay? That gets some expected amount of reward, and that is the value of policy pi. And now, among all those policies, there is some policy that receives the most reward, the highest value, and that's going to be called V pi star. And so to give you a picture in your head that might be useful is, there's a finite number of states and actions, and maybe you have a very toy sort of like situation where maybe you start in the top left, you have two actions, you can go left and right, and you're sort of ping-ponging down this board, and now your only reward is this far right action in this treasure chest on the right. But at any given state, in any intermediate state, maybe there's currents or wind, and so if you go left, maybe sometimes you go right. And this happens in some unpredictable way, yet you're trying to identify what is the right policy to identify this treasure chest as fast as possible. And again, we're interested in maximizing or minimizing the regret and identifying the epsilon good policy as fast as possible. Okay? And just for those of you that haven't seen this before, I just want to really emphasize how much harder this game is than the multivariate bandit game. Because recall, in the multivariate bandit game, it was actually okay to just uniformly allocate actions at any given time, right? If you just randomly played an action each time a patient came, it was slow. There was downsides to that policy, but it did identify an epsilon good policy pretty quickly. Eventually, it did work pretty fast. And it was a reasonable strategy to do. But when we moved to MDPs, doing that naive exploration of just randomly taking actions actually turns out to be catastrophic. And so if we just take this extremely simple MDP, where each black dot here is a state, and if we, it's a deterministic MDP, so nothing is random here. And so if I'm at this state, if I go left, I go down. If I go right, I go right. And now on this MDP, I'm going to set it up such that you get a reward. All rewards are 0, aside from if you get to this state here. And what's special about this MDP is that clearly the only way to reach this red state and receive some reward is to keep going left, 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 left. That is the only way to get any reward. Otherwise, you're going to get 0. If you go right at any point, you're going to end up in this absorbing state and receive no reward. But if you're playing uniform at random, actions uniform at random, that means I need to get h time steps in a row of always selecting left. And so if this MDP is h steps deep, clearly that's going to be happening with probability 2 to the minus capital H, which could, and so in expectation, the amount of time it's going to take to identify the optimal policy is growing exponentially in the horizon. This is really catastrophic, because what we really want to do is have very long horizon planning in planning for these MDPs. We want to be able to design treatments and robot policies and self-driving cars such that we actually can plan in a very long horizon way to figure out what's going to happen, and play optimally in those strategies. And so what we really want is the sample complexity to be more like polynomial in SA and H, not exponential in H. And so we really do need to do something a lot more intelligent than just random exploration. So what do people do? Well, there's a lot of grad students in the room. I'm sure you've interviewed for internships and things and spent a lot of time on LEET code. And so I'm sure you're all familiar with dynamic programming. And this is a very beginner's dynamic programming question. If I knew what the transition states are, these probability matrices and these reward functions, then what I want to do is I want to start at the end, at big time h, at the very end of this cycle. And if I'm started in some state s, what is the optimal action at that time? There's nothing else I could do at that time. If I'm stuck at big time h and I'm in that state, I just would take the optimal action at that time. And I lock those down. I fix those. And then I go one time step back at h minus 1. And I ask the question, well, now I'm stuck at this state s at h minus 1. I know what to do in the future. At the next time step, I know what the optimal strategy is. But I also know where, if I take a particular action at this point, where I'm going to go in probability, what states I'm going to go to. And so then I can also compute exactly what the expected cost is going to be, or the expected reward in each one of those states is going to be, and I can compute the optimal action. And I just, or the expected reward to go, and I just keep recursing this back all the way back to h equals 1. And then what I do for the optimal policy is I just define pi star as just the argmax of the q star of SA. Okay? This is the dynamic programming 101. And it is the solution to this problem. It is provably optimal by deduction. The problem is, we don't know what the p matrices are and the reward functions are. A priori, when we start this game, we don't know what this is. So what are we going to do? Well, if we did some amount of exploration, we're going to have some empirical estimates of these quantities, of course, even if we did some naive exploration. And so what are we going to do? We're going to do exactly what we did when we studied optimism, that UCB algorithm. We're going to plug in those empirical estimates, but then we're going to add a little bit to each one of these. We're going to add a little bit such that that little bit, this bonus term, this BH of SA, is going to be defined such that that confidence interval holds. But namely, all we really need is that when we define this Q bar, which is equal to the empirical thing plus the bonus, it has to exceed that Q star. And if you satisfy this condition, if you define the BH function that satisfies this condition, that is all you need to guarantee that this algorithm will, and the fact that the BH is decreasing in K, those two conditions alone will guarantee that you will converge the optimal policy. It's an amazing fact. It's totally not obvious why that's true. It takes a lot of analysis to show that, but it is true. And over the years, dating back to all the way back to Sean Cockaday's thesis in like '99, when he started writing down these problem statements, many dozens and dozens of papers have tried to analyze this problem and come up with stronger and stronger results. We finally, in 2017, had the first sort of tight result of this. If we play this algorithm, we choose that BH function correctly, we can actually get a regret bound that scales to the square root of h cubed SAK. Okay? And what we can show is that this is actually provably optimal, meaning there exists some worst case setting of this MDP, the worst case setting of the transitions, the worst case setting of the rewards, such that no algorithm can get substantially smaller than this. And there were, up until last year, there were also these additive lower order terms, and only this year did we actually get an algorithm that actually achieves this without any lower order terms, which is quite remarkable. It took 25 years to solve this problem. But it's a beautiful result. But it's a minimax result. It's a worst case result. It's a result such that it only says whether the MTP is an easy one or it's a hard one. Regardless, the guarantee only says that the regret is going to be less than or equal to that. It says nothing about if the algorithm, if it's an easy or hard MDP. And so it begs the question: is it also instance optimal? Is this same algorithm, is this very simple UCB optimizing algorithm, also instance optimal for regret? Okay. And so this is sort of the questions that we're going to be asking in the rest of the talk of what do these instance optimal results look like? And before jumping into the theory and how this stuff works, or what my work has done to answer these kind of questions, I want to loop back to how this relates to the real world, and how this relates back to robotics and these sorts of things. So if we loop back to this first slide of reminding ourselves of some of the high-profile successes of superhuman performance and gameplay that are so expensive, I want to talk a little bit about how these algorithms work. And in particular, one recent algorithm, this is now actually a couple years old. I really like this paper. It's a model-based RL algorithm. It's a deep RL, meaning deep learning, and it's extremely complicated, but it's a really beautiful algorithm paper. I recommend you read it. And I don't mean to pick on this paper, but one of the things it was able to do is, Minecraft is apparently a game that's very hard, and it got superhuman performance on Minecraft, which is very impressive, I guess. But for my purposes, I want to talk about this benchmark, this B suite. Okay? This is a benchmark that was designed by Osmond et al. At a DeepMind. And these algorithms are state-of-the-art algorithms for this task. And what this benchmark is really trying to measure is basically unit tests for different algorithms along different scales of how well is it generalized, how much memory does it take, or how much memory does the algorithm have, how can it scale, credit assignment, these sort of things. But the one I'm interested in is exploration. How well does this algorithm actually explore its environment? And this benchmark is designed to measure this. And I was very surprised to see that this algorithm that was doing so well on all these different benchmarks, or all these real-world examples, like Atari and Minecraft and these sort of things, totally failed on the exploration task on this benchmark. And what did succeed? What did succeed is this bootstrap DQN paper. This algorithm is a decade old and very, very simple. It's basically UCB. It's more inspired by Thompson sampling, but it's basically UCB. It's these bonus-based sort of things. And it seems to be doing very, very well on this task. Why did everything else fail so horribly? And so I want to understand what was the current state of, because this bootstrap DQN was doing so well, these other algorithms are doing so poorly, I came across this other paper that started looking at optimism algorithms. One of the main ways that people design these algorithms, these practical algorithms, is using inspiration from optimism and UCB of adding these bonuses to encourage exploration. And what this paper did is, unfortunately, reinforcement learning has a practical reinforcement learning has a terrible reputation of being reproducible. It costs so much to do these experiments. It takes so long, and it's so hard to get everyone on the same page with the benchmarks that it's very hard to reproduce. And this paper said, okay, we're going to make our own benchmark, try all these algorithms out, implement them, spend probably millions of dollars to re-implement these algorithms. And sorry, that was this algorithm. Sorry, I jumped a slide. This is still talking about what is this exploration task. It is just basically tasks like this or like that other MDP where you really do need to go like left H times in a row. You need to actually take an exact sequence of actions. You really do need to explore in a really good way. And what this paper that I was talking about a moment ago was doing is it tried to put all of these algorithms on the same playing field that were doing bonus-based exploration, and they found something extremely interesting. And I won't make you read that, but what it basically says is that when they tuned the algorithms, tuned these bonuses to be very, very good on hard exploration tasks, meaning tasks that you couldn't just fall backwards by like randomly doing things and finding the optimal policy. You actually had to really deliberately explore on this one game called Montezuma's Revenge, which is famous for this in the RL community. For this task, you had to actually explore. When they tuned the algorithms for that hard game with these bonuses, what they found is that when they put that algorithm that was tuned for the hard game on the easy settings, it failed horribly. Meaning, when it was tuned for the hard MDPs, when it was then tasked with an easy MDP, it performed about as poorly as it did on that hard MDP. Meaning it wasn't adapting to the true difficulty of the problem. It basically was only that regret bound we had, that worst case regret bound, that wasn't a more pessimistic thing. It really was performing as poorly as we think it was, as that bound was reporting. It was not doing any better on easy MDPs. And so that got me very interested in trying to understand really what makes a reinforcement learning problem hard. Right? If we look at two mazes, we start at the left, we want to go to the right. Clearly, the upper maze is going to be harder to navigate than the bottom one. But in a lot of this literature, when we're just counting the number of states and actions and time steps, these look the same. The sample complexity of these problems is acting like SAH cubed over epsilon squared. These look the same in terms of these worst case regret bounds. Yet one is clearly easier than the other. And so what I wanted to do in these next series of papers is try to quantify what makes an MDP hard, and can we design algorithms that provably adapt to it. And that is going to call this instance-dependent sample complexity difficulty. Okay. And moreover, then my goal has never been to try to get the best state-of-the-art sample complexity bounds. I mean, that's partly what I'm trying to do, but what I really want to do is try to understand what does optimal exploration look like. We are human, living, sentient things. We are navigating this environment without even thinking about it. We learn to do things without even thinking about it, yet we're extremely good at it. How do we automate that procedure? How do we automate exploration in these environments where we can take different actions, get new updated information, and take new actions? What does an optimal exploring agent look like? And that's what I really want to focus on in the rest of this talk. And that's what I focus on in my research. And again, the reason why this matters is because we don't have simulators for everything. We need better algorithms to be able to do efficient exploration when we have to be doing that exploration in real time on real patients and in real robotic applications. Okay, let me pause here and see if there's any questions on anything that I've said or where we're going. Yeah?
I wonder if you could just say a bit more about those two mazes and why these would be seen as being as difficult as each other.
So if we go back to those regret bounds that we had, this regret bound I had on this slide, so the regret for this MDP was square root of SAKH cubed, where S is the number of states, A is the number of actions, K is the number of time sets, H cubed is the number of the horizon. And so for these mazes, what's my action space? Up, left, up, down, left, right. The number of states is the number of sort of locations in these mazes. And so the number of states and actions for these two mazes are identical. And so in response to just that bound, these look the same, but clearly one is easier than the other. Yeah.
So as the measure of difficulty, could we intuitively try to say, estimate how many solutions this thing has? And if it has too many solutions, it is easy. And if it has too few solutions, it's also easy.
That's an interesting question. So there is a notion of, so I think what you're getting at is the fact that like if there's many ways to solve the maze, that's going to be an easier problem than if there's only identically like one way to solve the maze. That could be true. That's one notion of difficulty. But it turns out that that's not going to be, that's actually not the dominating factor in what we'll see. It really has more to do with how do we get to these different states and how do we explore and how do we eliminate different policies.
But if you have paths request, right, then it's like most of the paths lead to dead ends.
So yeah, I mean, if you can naively explore and find one of these policies, one of these good policies, that'd be great. And honestly, that's what a lot of these very naive exploration schemes are relying on. That if you just follow your nose, you're eventually going to, going downhill, you're eventually going to converge to the optimal policy. But with a lot of these algorithms where, it's helpful sometimes to think about games and things. Like sometimes you need to go to this faraway place to get a key, to go back over here to get a lock. There's no clear reward signal along the way telling you that you need to go all the way over there to go back to the box. And so it's those kind of games where just following your nose of getting the immediate reward, accumulating as much as you can, is not going to help you get to the end, more far-reaching goal.
I might be jumping ahead. I'm wondering, is there going to be one definitive answer of this is how you should measure difficulty, or could there be 100 reasonable measures that each have their pros and cons?
I will claim there's one.
Okay, I'll see if I can mislead.
I would say there's one from an information theoretic perspective. Yeah, I'll get to that. Yes?
What's the difference between the horizon and the peak?
Yeah, I'm sorry. The notation MDPs is very confusing. And there's just so much of it. It takes a very long time to get up to date on this field because there's just so much annoying notation. I'm trying to spare you from it. So H is the amount of time steps for an individual patient. Okay, when I show up to the hospital, I am going to be treated for H time steps. K is the number of patients. Okay, and so I get to play this game K times, but when each individual game has H time steps to it. Okay. Yeah.
I understand that in many of the examples that you went through, and majority of the ones that you see elsewhere, the set of states is fixed.
Yes.
Finite, discrete set of. But throughout observations, as we play the game or we deal with the patients, you might identify new states. So is this something that you're going to talk about, or is this going to be definitely changing the complexity of one problem to the other problem? Because initially we hypothesize that there are these three states, but then we discover more to be able to find the optimal solution.
Yeah, so in the beginning, a lot of these optimal algorithms don't rely on knowing the number of states ahead of time, and they can discover them as they go, and it doesn't really change how difficult the problem is. What really governs the difficulty of the problem is how hard it is to get to an individual state. Because if these transitions from one state to another is a stochastic process, it could be the case that it can be very hard to get to a particular state. Right? And then the reachability is actually going to be the factor that's going to determine how hard an MDP is, not so much the number of states, although it will tend to scale with that.
Initially, we don't know that state even exists.
Nope. It won't matter. These algorithms adapt to it. And not knowing what states are, or having a state being really rare, is equivalent to having like a patient with extremely rare symptoms. We'd love to have more patients that have those extremely rare symptoms, because then we could explore more. But if it's just extremely rare, then we're just out of luck. It's just hard to get to that particular state of symptoms. And that's going to influence how difficult it is to solve these problems. Okay. And so what we're going to talk about in the second part of the talk is talking about these instance-dependent sample complexities, algorithms that provably adapt to the true difficulty of the problem of MDPs. And as Reza suggested, we're looking at finite states, finite actions. This is a very simplified problem. This is it is the simplest possible MDP problem I can talk about while still being interesting. A lot of the stuff that I'm talking about today can be extended to more complicated settings with functional approximation, deep learning, these sorts of things. In fact, a lot of those algorithms are directly inspired by the algorithms that are developed for this very simple tabular setting. It just becomes less tractable to say anything very concrete, and this is a very solid things that we can talk about. But okay. So the first paper I'm going to talk about is trying to go after this question of, we saw over here that the regret bound was the square root of SAK, and it was not instance dependent. And like, how did the individual performance of that MDP, can we adapt to that in a regret sense? And I said nothing really about PAC, learnability. I said nothing about, sorry, shouldn't use that word. I said nothing about epsilon good identification of a policy. And we'll get to that in a second. So this is joint work with my close collaborator, Max Simchowitz. Started working with him in Berkeley when he started as a grad student, but he just recently started as a professor at CMU this spring. Okay, so I've just rewritten what the MDP process is. Nothing is new here. It is just familiarizing yourself with the notation or reminding you of the notation that we're interested in here. And now there's one more piece of notation here, which is the gap. In the Mothar and Bandit's case, we had this notion of a gap between the optimal action and the eighth action, right? But now that we have this MDP, what is the right notion of gap or suboptimality gap? And it turns out to be this quantity here. So a V star of S is the amount of reward that you would get from the optimal policy if you started at state S at time H and went to the end. And Q star is that same thing, except what you're going to do at time H, you're going to play action A, so deviating from the optimal policy. But then when you transit to the next state, you're going to then play the optimal policy. Okay, so it's a one step away from playing optimality. That's what you should think of the Q star function as. If V star is what the optimal policy gets, Q star is I'm going to deviate for this one time step, play action A, and then follow the optimal policy for the rest of the episode. Okay? And so because you're deviating from the optimal policy, this is always going to be a positive value because you're deviating from the optimal policy. And again, we're going to be analyzing optimism. And we just showed that this algorithm gets the square root of h cubed SAK. And the big question is, does this algorithm also suffice for regret, for instant optimal regret? And it turns out that the answer is yes. The same algorithm that achieves this minimax result, this worst case result, not too surprisingly, is also optimal in an instance-dependent result, in an instance-dependent sense. And this can be seen from this result here, where now, just like in the Mothar and Bandit sense, where you had the sum of inverse gaps for the means and the gaps, these same gaps show up here, the appropriate notion of gap. In this second term here, it's unavoidable, but I don't want to talk about it. Same algorithm as a fallback guarantee because it was this original algorithm. This min-gap term cannot be removed. And it also matches known lower bounds for large classes of MDPs. Interesting fact about MDPs is that we can write information theoretical lower bounds down for how hard these problems are. And that problem, that number that comes out of that, tends to be actually the solution to a non-convex optimization problem. And this is very interesting and very damning in a way, because if we hope to be optimal, it kind of suggests that we need to be solving a non-convex optimization problem provably. And that's pretty scary. We don't know how to do that. But what we can do is we can look at a large class of MDPs that we care about, and this matches that rate on all those classes that we know of. So it's as good as we can possibly get, in my opinion. Okay? And so this is a quick sort of thing. Yes, the same old optimism algorithm works for instance-dependent regret as well. Yay. And so to summarize here, to give you a picture of the lay of the land, we hear this very basic optimism principle that's just been used over and over for the last decade and a half, 2 decades and a half, is we're provably optimal for regret in a worst case and instance-dependent sense. It's provably optimal for regret in a worst case and instance-dependent sense for MDPs. But what about for epsilon good identification? Because I want to point out, regret, while it's a very intuitive notion and it's very well accepted by the online learning community, I have a whole other talk that's a huge rant about how I think regret is a totally fake thing. Almost never is regret used in practice. And the reason why is because you almost always have a baseline policy that you like already. And you never want to deviate away from that too much. But also, a lot of these trials, these gameplay sort of things, they're trying to find a good policy. They don't care what is the amount of regret you get along the way to that policy. Clinical trials, they're only trying to optimize for the performance of statistical power. They're actually not trying to minimize regret because they want to touch as few patients as possible because each patient is so critical. They do not have the sample complexities that they'd like. And so, while optimism is really great for regret for both MDPs and bandits, the story for epsilon good identification, which I argue is actually the right objective, is still misunderstood. And so this is a paper with my student Andrew Wegenmaker, who just graduated. He's now at Berkeley, and Max is at CMU. And so this is the same setup. And now we're trying to find epsilon good identification, also known as the PAC-RL setting, where PAC stands for probably approximately correct, if you're familiar with learning theory. But you don't need to worry about that. I'm just going to call it PAC-RL. It just means identifying epsilon good policy. And now we have this regret result. And just like with our multi-learn bandit setting, if we have a low regret algorithm, this immediately implies a good identification algorithm. And this makes sense. If you're getting low regret, that means you are converging to the optimal policy. So therefore, you have to be able to have found a pretty good policy. And so if we choose this pi hat uniformly at random from all the policies that we've played, then by the same exact calculation, we see that the quality of that policy pi hat and expectation is equal to the regret over k. So set that equal to epsilon and solve for k. Okay? So if we do that, we immediately get a PAC result from this regret result that looks like this. Okay. We've done nothing. This is just an immediate corollary. Now, the good news is that this is somewhat instance dependent. It has the gap showing up there. If it's easy, that's great. The bad news is that if epsilon goes to 0, this bound explodes, which is nonsensical. At some point, if the optimal policy is unique, I should be able to identify it in a finite number of samples. And so we know that this bound is wrong. This cannot be tight. And again, to give you the lay of the land, in bandits we found that optimism, this very simple algorithm, was optimal for regret, PAC, in the worst case, in instance dependent. Oh, I ruined the punchline. But for MDPs, it turns out that you can prove that this in the worst case sense, optimism is also optimal for PAC. And the only question remaining is this instance dependent result for PAC, which again I was just arguing a moment ago is the real question that is on everyone's mind. And it turns out that is not true. Optimism is insufficient for this process and is actually arbitrarily worse. And so I want to go through in the next few minutes exactly why that is. Okay, so in the next few minutes, you're going to see a lot of really ugly expressions like this. I don't want you to focus on them too much. They don't really matter. The exact form of how these exploration terms come up is not super important, but I want you to focus on how these algorithms actually behave. Because we know how optimism behaves. We know this is insufficient. How do we make it work? And so the sample complexity tends to act like this phi of epsilon, which is really, really ugly. And this new algorithm, MoCA, that we came up with, satisfies this theorem. It's provably never worse than the minimax rate, so it's never worse than the worst case best bound. It's never worse than that regret to pack bound that we just did, that corollary on the last slide. It's always better than that. And then also, for epsilon equals 0, meaning for the optimal identification, the optimal policy, if we want to identify that one, then it's actually provably optimal. Nothing can improve upon this. So for the epsilon equals 0 case and delta going to 0, this is actually provably optimal. But those are two very big caveats. Because in the real world, both delta does not go to 0 and epsilon does not go to 0 either. Because the number of policies is exponential in S and A. Like you're never going to identify just a single best policy. There's always going to be some tolerance epsilon that you'll have to give up in identifying. So we want to focus on how does this algorithm actually work. Oh, and this is just that proposition saying that yes, you might have thought that maybe optimism is instance optimal. We just did a bad analysis of it. Maybe we're just not good enough to analyze this thing. And actually, that's not true. We can say something extremely strong here, actually. Any algorithm, not just optimism, but any algorithm that gets low regret necessarily is arbitrarily worse at the pack problem, at the epsilon good identification problem. And we can say this by saying our algorithm has an order 1 sample complexity in terms of epsilon on this particular MDP, yet any algorithm that gets low regret necessarily suffers a 1 over epsilon.
Low meaning sublinear. How low is low regret?
Good question. Anything that's t to the 1 minus epsilon for any epsilon greater than 0.
It could be really suboptimal. It could be way far from the optimal, but it's still like low enough for this to hold. Yeah.
Yes. Yeah, it is a very bad idea. And the intuition behind this is basically any low regret algorithm, once it identifies a state to be suboptimal, it will stop going there. But in the real world, a lot of times, what you want to do is you want to go to a state because that might give you access to all other states in the MDP. And it might be very, very advantageous to go to accept bad returns in the short term for a lot of returns in the long term. And how does the algorithm work? Just a quick, what is the intuition behind how the algorithm works? Is that basically if you call the multivariate bandit setting, we knew that you can identify an epsilon good policy or epsilon good alternative in the multivariate bandit setting, which is the sum of the inverse gap squared and 1 over epsilon squared. And if we think about what tabular MDPs are, they basically are a bandit at each state and time. Right? They're just a simple multivariate bandit at each state. The difference, though, of course, is that the current action you take now influences what state you go to in the future. And you care about the summed amount of rewards, not just the instantaneous amount of reward at the current time. And also, most importantly, some states can be very hard to get to because these state transitions are stochastic. If I'm at this state, there could be 0.1 going to that state, 0.2 to that state, 0.8 to that state, whatever. And so it could be that some states are just very, very hard to get to. And so if you define this quantity W pi of h, of S being the probability that policy pi visits state S at time h, then what you can show is that you don't need to learn the optimal action at each state in time up to tolerance epsilon if you just want epsilon good policy. It suffices to actually learn up to tolerance only epsilon over WH pi star of S. Okay? What this means intuitively, if the optimal policy doesn't go to a state, you don't need to learn it. Right? If it's very hard, if the optimal policy never goes there, it really doesn't matter if you need to go there. Or, moreover, if no state can go, if no policy can get to a particular state, you don't need to learn that state either. And what this translates into, if I only need to learn a state up to that tolerance, which is far, far greater than epsilon, that's going to translate into a much, much smaller sample complexity intuitively from a multi-bandit perspective.
I think I must be missing something
Yeah.
here. The state visitation probability is essentially the probability that you would visit a certain state at an age.
Yes.
So if the state can't be visited, that probability would be 0.
Correct.
So that would mean that you would have to learn this up to infinite error, right? No?
Yes. Yeah, technically, yes. There will be a indicator here that you can actually reach that state. Or said another way, yes, meaning that you can learn that state up to infinite tolerance, meaning you don't need to know it's extremely large error in that state. So if it's very hard to get to a state, that means you don't need to learn it. Okay, so if it's going to 0, then that means you don't need to learn that state. Yes, exactly. Yeah. Okay, so we don't know what the optimal policy is, so we're going to learn it up to the supremum over all policies pi, because we don't know what the optimal policy is. Okay, how does the algorithm work? Yes?
You just said that very casually. That sounded like a loose step to me.
Well, John, it is a loose step. Yes, it's extremely loose. I don't know. It depends. It's loose.
Totally garbage policies that, yeah, I don't know.
We're going to throw this algorithm out in a moment, so don't worry about it. I just want to give you intuition. So how this procedure works is each one of these red dots is going to be individual state. You're going to start at h equals 1. You're going to go to this state. You're going to take some action. You're going to transition to some other state, and you're going to go through this process. And so fix some expiration pi in. Say, don't worry too much about what it is. It's some policy that explores this MDP. Don't worry about where we found this policy, but we have it. And what we're going to do, we're going to play this policy pi in all the way until we get to the last time h equals h, big H. And at each one of these states, here, at each one of these states, they really are acting identically to a bandit. Because when you play an action, you just get the reward and you're done. Right? And that you're playing the optimal thing at that point. And you're going to have, the amount of sample complexity you're going to pay is exactly the sample complexity here, which is copied from that last slide. Because you only need to learn up to that tolerance, which is this sup pi over w pi of h. But we have to pay for the fact that you have to get to these states. And so you have to pay for this inverse 1 over pi in of s. Because you have to get to those states, it's very hard to get to, and so you have to pay for the amount of time to get there. But then once you've fixed the policy pi hat at that last stage, you then are going to be playing that policy at that stage, and now you're going to redo the whole thing again at this last h of minus 1, treating those as bandits. Okay? Each one of these is bandits because then once you play that action, you're just going to play the pi hat at the next round. It's a stochastic process. It's an IID process. Because you've locked down all dependencies in the future. And then you just back out all the way to the end. And then you end up with a sample complexity that looks like this, which looks suspiciously like phi of epsilon, which was that ugly expression on that first slide. So that's where it comes from. The policy pi in is actually, how we come up with this is actually one of the more technical, interesting things of this paper. It's from Reward Free Learning. Ask me about it some other time. It's too complicated to describe it here, but it's a very interesting part of this paper. Okay, and so with this what this expiration policy was doing, it was basically doing dynamic programming, right? It went to the end and then played bandits and did action elimination. But it's very sort of naive, and it got us thinking when I'm at Amazon, how things actually work is you don't have all policies under the sun to optimize over. how things actually work is engineers give you a finite set of policies or some parameterized set of policies and say, hey, we think these are pretty good ideas. We don't know the exact hyperparameters or how to satisfy these policies, but we know something in this set is going to be pretty good. And so it got me thinking, well, what if I had a finite set of policies, pi, not all policies, how does that change the problem? Because I clearly could not do this last algorithm. And so this motivated me, or us, to study this setting. And the intuition here is that if we look at v pi, the value of policy pi is just the summed rewards. Well, we can talk about that as we can consider the state visitation probabilities of each policy pi and state actions. And then we just take the inner product between where that policy goes and the rewards that were achievable in all the different states. Very simple calculation. And moreover, these state action visitation probabilities are very easy to compute recursively. You just start with what the initial probabilities are, and you just have a push forward measure through your state transition matrices if you knew what they were. Of course, you don't know what they are, so you replace these quantities with empirical quantities with some amount of data that you've collected so far. And so with this procedure, what you're going to do is you're again going to have some pi in. You're going to run this pi in, but now you're going to start at the beginning of the MVP, not at the end. And what you're going to do is you're going to set some small epsilon 1, and you're going to learn all policies, the performance of all policies, or this inner product between R and the state visitation probabilities up to tolerance epsilon 1. Then you're going to see how every single one of those policies transits to the next state and tries to figure out where these policies go. So instead of like the other scheme where you're doing action elimination, where you're trying to figure out what's the optimal action in every state, here the whole process is always just focused on the dynamics. You're only trying to figure out where the policies go, and then all the rewards and that sort of thing is always just an afterthought. It's always going to be low order terms. And we're just going to continue this process over and over until we get to the end. Now, because we've estimated every policy up to tolerance epsilon 1, we can then just eliminate all those policies that are more than epsilon or 2 epsilon 1 suboptimal. And now we have a reduced set of policies, and then we can have epsilon 1 to be epsilon 2, and then rerun this process again. And so we're doing this very policy elimination sort of strategy. And if we add up all those sample complexity terms, we're going to end up with a term like this. And again, we get to inf over all exploration policies pi in by a very clever scheme, which is basically this online Frank Wolf algorithm, which is beautiful. But again, it's too technical to get into right now. Okay. And so now we have 3 very different exploration ways for these MDPs. We know that the first one's suboptimal, optimism. And then we have these action elimination and these policy elimination style strategies. They are clearly different quantities. Can they be related? Which one is better? Unfortunately, neither. We can come up with 2 MDPs such that in one MDP, the first algorithm is great, and another MDP where the second algorithm is great, and neither are superior in both.
Are we not worrying about computation at the moment?
No. Just statistics. Yeah.
Policies is crazy. Right? Yeah.
Yes. Yeah. Enumerating the policies is going to be very hard. And so I'm an obsessive person, and so those papers were published a couple years ago. I thought about very little else aside from this problem, and eventually convinced co-authors to work with me on it. And we finally came up with a slightly different algorithm. So this was the last algorithm sample complexity copied here. And what I'm going to do is I'm going to call delta pi epsilon just to be this max of the gap and epsilon. And I'm going to rewrite this totally equivalently, but much cleaner as this. Okay. After this paper was published, El-Marjani, Terzoni, and Kaufman showed a lower bound for this problem of this term. And it looks suspiciously like that top term. But it has this sort of reference policy. It subtracts off this reference policy pi star. And so we worked and worked and worked. And then we finally came up with a sample complexity that looks like this. And so we match on this first term, but then they don't match on this second term. And the way this, the interesting sort of questions to be asked are, does this second term that is not in the lower bound, is it real? And what are the new ideas to achieve this algorithm? And it turns out that, yes, the lower bound is loose. The lower bound is loose in the sense that if you just had, there exists some MDP that that first term is very, very small, but there's some other term that's extremely large that can be characterized by that second term and must be there. And then second, for the contextual bandits problem, if you're familiar with that, these bounds are matched in the lower bounds. So it is tight. And the intuition behind this, and this is where it actually gets starting to get interesting with practice, is it turns out for MDPs, the hard part of MDPs is actually estimating where policies go. It's actually learning the dynamics. And that first algorithm that we talked, or that second to last algorithm that we talked about, what it was doing is it was trying to figure out where all the policies go simultaneously, individually. But it turns out that if you have a reference policy, if you have a baseline policy that you learn really, really well, if you have a baseline policy that you learn really, really well, it turns out that it's much, much easier to understand how other policies just differ from that policy with a much variance-reduced estimator. And if you do that, you get a variance that looks exactly like this in the numerator of these two expressions, and that's exactly where the sample complexity comes from. It comes from the fact that you're actually trying to learn a single policy really, really well, where it goes, and then only estimating the differences from where policies differ from it. And so right now, what we're doing is we're making deep RL algorithms based on this principle to actually implement this to see if we can get these superior results in practice. But I want to just emphasize that we are very, very far away from proving anything in more interesting deep RL settings. We have everything I've said today actually does extend to linear MDPs, which is a tractable class of parameterized MDPs with infinite states and actions. But it is still a far cry from, say, the Dreamer v3 algorithm, where you can work on images and things like this. And so it's a very exciting area. I hope if you knew nothing about reinforcement learning, you've learned a little bit today. And if you knew a lot, I hope you can appreciate some of this work. And so thank you for your attention.
Question? I might as well follow up on the one I just said, like how, even in the tabular setting, how much statistical and computational gap do we have?
Huge.
Like, so we don't have anything close to getting these efficiently?
No. So yeah, this is a major problem. Okay, first of all, tabular MDPs are not like that real of a problem. They're such a sort of like a toy problem that it's not like where people are trying to break down the door, needing better algorithms for that specific setting. Again, people study tabular MDPs because we want to inspire algorithms for the deep RL settings or the more function approximation settings. So at this point in time, I'm not like critically obsessed with computational performance, because what people actually do is we don't run algorithms that look like these. We'd run algorithms that are very much inspired by these. And you can run algorithms that are, from a Thompson sampling style perspective, that are very computationally efficient. And so this algorithm I set up we were developing is very computationally efficient and is very well approximated by these ideas. Okay. And so, yeah, a lot of my work is really trying to understand the statistical aspect. And to your other question of, is there a right answer? I'm saying like yes from the perspective that there are known information theoretical lower bounds, and we can match those information theoretical lower bounds. Okay. And so that's really telling you what are the interesting parts of the MDP that make it difficult.
I was vaguely thinking like these expressions get a bit complicated, hard to interpret. Like, could there be interest in giving up some looseness, or like being a bit looser to gain some interpretability that maybe practitioners prefer?
I mean, I think they're beautiful. I think, okay. I think they're very interpretable. But I mean, they're not for everyone.
Yeah, no, they're not that bad. Yeah. Like,
No, I mean, in all seriousness, yeah, they're difficult to interpret. But if you're deep into it, these all have very interpretable meanings. But yeah, I don't know what to say.
I mean, I guess even if you had something much more interpretable, I don't know if it would actually help you design things in practice. Like, yeah.
But I mean, I think a lot of this is like.
It's just a thought. Like, you couldn't give this to a doctor, let's say.
Well, I mean, I don't think we need to. Yeah, doctors should not worry themselves with
They
SAM
shouldn't have to worry,
complexities.
yeah. Yeah,
They should
okay.
worry themselves with what does the exploration policies look like.
Okay.
And I think that's the main takeaways of this is not so much what does the SAM complexities look
Yeah,
like.
makes sense.
What are the results?
Okay.
Now I have to choose between these options, and this is sort of speaking as an outsider here.
Yeah.
Because we've tried to play around with NADs and all of these things, and you're dead on. This regret thing is just almost never the right thing to go on. So what do you recommend? Which from your list is the one we should pick for sequential hypothesis testing?
So it depends very heavily on the particular structure of your problem. The tabular MDP setting is so general that it's it's almost like you're making the problem too general and hard. If you have a real setting, like a real problem in front of you, you have an enormous amount of structure in that problem probably, and that you want to exploit that structure. So like a lot of this work is actually directly inspired by work I was doing at Amazon Robotics, but like you better believe that we're not implementing these algorithms. They're algorithms inspired by these, but we're exploiting a lot of additional structure that we have in those problems. And so it's for any real world problem, it's usually a one-off solution that's going to be efficient, which is not the most satisfying answer. I know.
Okay. Okay. Maybe we'll have one more because it's coffee break time after that.
What does it mean by exploiting structure? So suppose let's take the regular setting, right? Then there could be actually, if you look at the full table, you could maybe understand this table. That there could be some formula which explains this table.
Yeah.
But your algorithm doesn't use this. Right? So what do you mean by exploiting structure?
Exploiting structure could be things like exploiting monotonicity. Like I know that if I take this action and it's bad here, if I keep ramping up that action in some direction, it's only going to get worse. Or things like this. It's exploiting structure. Like I know the laws of physics, and I know that there are just limits on how fast things can move, and I should rule out any physics or any transitions that would disobey the laws of physics. Trying to incorporate those kind of structures that you this side knowledge to try to greatly reduce this state and action space.
How does that feed back into the algorithm?
In a couple ways. You can do it through restricting the space of transition matrices. So that's a more model-based perspective where you're trying to actually model the world. A different way of doing this is through being more agnostic about how the world works, but then putting that side knowledge into what policies you define and define over. So you can say like, I know the optimal policy is going to have this kind of form, so I'm only going to search over those space of policies. And so these are two different, somewhat competing worldviews on how to solve reinforcement learning problems. Do you optimize the dynamics, or do you constrain the dynamics, or do you constrain the policy space, or both?